is something that is viewable. Are we recording? Yay. Okay.
Oh, sorry. So the basics of integration. All right, start with a graph, a nice picture. Pictures. Integration is best understood through visuals. So let's say I've got the velocity of some particle at some time. So this is v of t, the velocity of something. If I'm up here, that means it's moving forward. And this is like a thing on a line. So you can kind of think of this. Here's a wire, and I've got a bead on the wire. Some kind of self-propelled bead, some mystical bead that's able to move somehow through some propulsion. And if the bead moves this way, that's positive velocity. And if the bead moves this way, that's a negative velocity. And the rate at which it moves is the magnitude of the velocity. Positive and negative to the left. Sound okay so far? Cool. So let's do some thought experiments. And if you were in Calc 1 with me, these thought experiments will not be novel to you. So at time 0, here's when I start my thing. So here's time equals 0. And then here's, let's say we're in seconds. And good Lord, how about some units? This is meters per second. Here, here's 1, 2, 3 seconds. And I just see this happening. The velocity is constant for 3 seconds. And let's say that that's literally, let's pick a nice number, 11 meters per second. So the picture that this goes with is this bead is moving to the right at a constant rate. As opposed to right? So we're just cruising, and we're not changing. There's no friction, there's no extra propulsion, we're just rolling. That's what we got here, and that's happening at 11 meters per second. That is freaking fast, right? Like what's 11 meters? Longer than this room? Probably 33 feet. Yeah, in 1 second. Right? That's like close-up magic fast. Get that shit going. So my question is, how far did I travel? What is my displacement? Now this is a very easy thing to do here because we're kind of used to working with some basic things. But the question that we want to ask is, what is our total displacement from t equals 0 to t equals 3 seconds? I've almost killed myself on this twice. Let's fix that. And after not speaking all summer, my voice, I'm a little out of throat shape. Yeah, you gotta get worked back up. I'm very quiet, like at home. Like my wife and I, we like silence. We don't talk much. And that's not a bad thing. You know, that could be a bad thing, but it's not for us. We like it that way. It's a very quiet lifestyle. Where the hell was I? Okay, yeah, sorry. My throat is bothering me. That's the key thing. So what is our total displacement? Can someone help us with this? What do we do? Okay, here's the bead. Here's t equals 0. Where is the bead on this wire after 3 seconds?
33 meters.
What's that?
33 meters.
How'd you get that? That's great.
Well, I mean, it's just moving steady velocity, so it's just going to move over 11 per second.
Beautiful, right? So every second, this bead moves 11 meters. To get the distance it's traveled, John took 11 meters per second and multiplied that by the time, right? This is how I did physics. I see that there's a second that I could, if I multiply by seconds, then I just have meters, right? That's how I did physics. And I do that for 3 seconds, then the seconds cancel, and I've got 33 meters. We just multiplied. What we did was we took the time times the velocity, and notice that that is also the area of this rectangle. So the area of this rectangle is height 11 times base 3. Does that make sense? That was 33 in this nice simple scenario. So after 3 seconds, I know exactly where I'm at. So t equals 3. And let's say this is 0 meters right here. We are at 33 meters down the wire, literally. It's not too bad. Is this making sense? And if not, when I'm asking this, please, if you have a question, I guarantee you you're not the only one. 100% guarantee. All right, cool. So, multiply. Oh my God, I told you. I told you this class was about multiplication. We're gonna have to like bring in a pot of coffee. I see everybody's like, you know, it's okay. It's all good. It's like lots of yawns going on here. How can this not be like? How can your adrenaline not be going? Because this shit's gonna get crazy. So this is scenario 1. It's pretty straightforward, but it's not very realistic. Because when you get in the car, you drive somewhere, you don't instantly hit the velocity. You're not going 65 instantly. You don't go from 0 to 65. You actually accelerate, and there's a whole range of velocities that you acquire as you reach your terminal velocity. So what if I had something like this? Whoop, that I don't hit the 11 meters per second for 3 seconds, and I'm building up toward that. Now it's much more complicated. Now the speed's going like this. 0 velocity, speeding up, and then super fast. So it gets faster the further it moves. Seems almost intractable and unsolvable to figure out what that would be, but calculus to the rescue. So watch what we're going to do. Now you might just say, well, just take the area. You'd be right, but let's understand why. So what I'm going to do is first cut this into some smaller pieces. So let's make an approximation of how far we've traveled. So first I'm going to cut this axis into 3 equal pieces. And at that point, I kind of have to figure out a representative velocity for that entire interval. So here I'm just going to work with the right, say, okay, let's see. This would be like 11/3 meters per second right there, because that's 1/3 of the way across, and that's 1/3 of the way up. And then this would be 22/3 meters per second right there. And I'm going to say, okay, well, let's just assume that for that whole time, I was actually constant. I had a constant velocity that whole time. So assume that on these little intervals, you had that constant velocity of 11/3 meters per second and 22/3, and then this is 33/3 or 11 meters per second. So what I'm trying to do is just get back to the basics, because that rectangle was so happy and beautiful. And to find how far I traveled with that rectangle, I just got the area of the rectangle. I took time times velocity. And that's the idea here. We're getting an approximation. Will this be more than the truth or less than the truth? Or how will it relate to the truth? How does it seem? What do you think? Well, okay, let me do it, then maybe you can tell me. So my approximate distance, here's our first approximation. If I can spell distance, is going to be how far approximately I traveled over the first second plus over the second, plus over the third. So the approximate distance is going to be the area of this first little rectangle, which is height, 11/3, times 1 second, the base. So this is height times base. Just doing that little rectangle. Next rectangle, how far did I approximately travel over this next second? Well, I was going 22/3 meters per second for 1 second. So again, it's height times base. So here, notice my base is 1 unit across. And I'm turning this all into something about rectangles. And so then the very last one, right, is going to be the velocity 11 meters per second times that 1 second. And now what I have is my approximate distance traveled. So that's going to be what? 22 meters. Did I travel 22 meters or more or less?
You would have traveled less.
I actually traveled less, right? Yeah, exactly. Because check this out, these are all overestimations. This is like assuming I was traveling at the max velocity, like instantly. But I wasn't traveling this fast the whole time. I was actually traveling slower than that most of the time. So this thing right here, absolutely, John, this is an overestimation. Let's do this a different way. Let's get the same picture up. Do this again. Just get your same picture. So we've got 1, 2, 3, and here's 11 meters per second. Yep. And then I got my graph. Nice straight line. And now this time, instead of overestimating, so like on this one, the first time I said, let's assume I was going the fastest I will possibly go the whole damn time. Well, let's do it a different way. Let's say we're going the slowest the whole time. So on this first interval, we started at 0 meters per second. Let's just say, well, went 0 meters per second the whole damn time. That's an estimate. Now that is clearly an underestimate, but it's an estimate. It's okay, we're gonna make this all better. Calculus isn't gonna let us down. It can't. It's what keeps my sanity together, that calculus still works. There's one fucking thing in this world works. Calculus. Maybe a couple others. Physics too, I guess. So then the next one, notice here, I picked my velocity at the start of the interval. And then this one I'm gonna pick that, and I'm going to say, okay, well, I was constantly going that speed. Well, that speed right there was 11/3 meters per second. This was 0 meters per second. And then on this last one, I was going however fast I was when I entered that interval. And that was 22/3 meters per second. How far, what's the estimate? Ew, it's wet there. That's creepy. How far did what's the estimate here?
11.
What's that?
11.
Yeah, nice. How'd you get that?
Well, you do 0 times 1 and then 11 base times 1, 2 base times 1, add them up.
Beautiful, beautiful, Olivia. Awesome. So Olivia's catching the drift here that we're adding the areas of these rectangles up to get that estimate. And so this first rectangle, this guy here, this individual here, has a height of 0 for 1 second. So this is base, and this is height. Plus, this one here, I had 11/3. That's my, sorry, I got this asked backwards, sorry. Height times base, sorry. I'm doing it backwards. Height times base here is 11/3 times 1. And then here, height times base is 22/3 times 1. And our dear friend Olivia just added those up. It's 11/3 plus 22/3, it's 33 freaking thirds. It's 11 meters. Wow, that's quite a range of estimates. We won't be getting satellites landing on meteors or comets with this kind of math. We won't be doing much with this kind of math. It's pretty inaccurate. Any suggestions on how I could take these two and maybe get a better estimate? Just these two numbers. I got 11, I got 22. Where do you think the truth lies?
The average.
The average. So this is a severe underestimate here, right? I mean, the particle we're assuming didn't even move for the first second. That seems a little bit off. So we would expect this to be an overestimate, excuse me, an underestimate, a terrible underestimate. And so Olivia suggests that we add these two together, so here's a better estimate. We take those two equals the average of those two. Two terrible estimates, but so it's 1/2, 22 plus 11, 33 halves meters, which 16.5 meters. Okay, that's one way to get a better sense of what's happening, but it's not, it feels right, but we don't know that it's right. So here's what we're going to do, and here's Calc 2. Here's calculus integration in a nutshell. What we're going to do is cut finer rectangles. So right now I got 3 rectangles. If I made more rectangles, I would have a better estimate, and that's the name of the game. So what we're going to do, so better idea, is use more rectangles, refine the estimate. So what we're going to do is have something like this. Got my situation. There's 11 meters per second. Here's 3 seconds. What I'm going to do is cut this axis up into a lot of pieces. They don't even have to all be the same, but they're looking like it there. On each one of these pieces, I'm going to assume the velocity was constant. And so what I get is a bunch of rectangles like this. Here I'm actually using the velocity at the right side to account for the whole interval. And I could have used the left. Last one, right there. That's getting pretty shitty. Try to pull it together. Good Lord. Okay. Got a bunch of little rectangles. Each one gives me the approximate distance traveled if I just take its base times its height, because it's velocity times time. And I'll get the distance traveled approximately on here. So what I'm going to do is find the area of each rectangle, which is multiplication, right? That's base times height. Base times height. And add them up. And that's addition. And add them up to get an estimate. What happens is the rectangles get finer. They start making more cuts. Let's say I tried to make like about 1,000 cuts right here. I'm not going to be here all day. Nobody needs to see that. But what if there was just an incredible number of rectangles here? What would the estimated area look like compared to the true figure here? Maybe I'm not saying that right. Do you see that as the rectangles get finer, it starts to look more like the actual shape itself? That's the idea I'm striving for here. That the more rectangles I pick, the more precise this estimate becomes. And I'm not gonna go grandpa my way through the internet and try to find things to show you. I'll have that for next time. But the key idea in this first thing in this class is that if I really want, and really all I'm after is the area here. Notice that if these got really fine, it would totally just be the area. So the sum of these areas is approaching the true area under the curve. And if this doesn't make sense, I'm going to say it like a gajillion times. And when we get to applications, understanding this idea is incredibly important for like first part of this course. What is the true area under a rectangle? What's the formula for the area of a rectangle, a triangle? Base, height, what's the area? What was that, Fernanda?
Base times height divided by 2.
Base times height, well, 1/2 base height? Yeah, beautiful. So the area of a rectangle is 1/2 base times height. What is the area of our rectangle? Base is 3. Height is 11. What's the area? 33 halves. Where's my true estimate? Is the average of these two somewhere? Oh, it's over there. There it is. It was the average of our estimates. So the truth ended up being right with our little initial plan to get that estimate worked out good, but it's just a fluke. We lucked out because that's a freaking triangle. That's all. We lucked out by geometry. Had the curve looked like this, all bets are off. So what if my velocity is this? So the bead starts off and it accelerates really fast and then slows down and then it starts going backward and then speeds up. What might that look like? Well, let's see. So I start off with maybe a 0 velocity and I speed up and then the velocity starts to slow down. This is still a positive velocity. I'm slowing down though. And at this moment I have stopped. That's 0 velocity. So stop, stop. And then I start backing up. And I do that. And let's say that that's the 3 seconds. Oh my God. Here's my velocity curve. How far did I travel? How far am I displaced? I don't know. But I can tell you this. The answer would be this total area minus this total area right here. So if we could somehow find area 1 and area 2, then the displacement is going to be area 1 minus area 2, whatever those might be. We need to find out how to do that, and that's what integration is. That's what we're going to do. So, any questions right now? This might all be kind of like swirling about. Aren't you glad we stopped for a few seconds at the beginning? Because I know I'm a maniac too. I know that. I have a sense of what's coming out of this space where I live. It's a lot. It's a never-ending stream of math. Good Lord, I haven't even started my notes yet. Cool, we're good. Good for now? All right. You'll see this all again. And in fact, you're going to see it right now done right. So let's talk about the proper thing to do here. Let's just talk about area. The first part that the first real hardcore thing I want to talk about are Riemann sums and the definite integral. Really one of my favorite stories to tell. This stuff we were just talking about, this like cutting things up into rectangles and estimating, the Sumerians were doing this. So the first civilization, people building pyramids. People who are long gone wrote in cuneiform, right? Little chips on stone. They were doing this. There is no freaking reason we can't. We are in a room made of synthetic things. We drive vehicles that mysteriously transport us to and fro. We live in an age of wonder. We can fly. The Sumerians did this. They had like chariots, horses, all sorts of stuff. But that idea, this idea is so deep in who we are. It's been around forever. And we'll get into how they used it more and more. I gotta tell you one more thing. They used this idea to predict the motion of Jupiter in the sky. And we always think about the first peoples is like, oh, the sun, what happened? Oh, an eclipse, oh my God, oh, I'm terrified. No, these people were computing the motion of Jupiter across the sky. They knew Jupiter was, I mean, maybe they thought like there was some, deity associated with it. Who gives a shit? Could you? I couldn't. I would not know where to start. Here's your homework for the weekend. Just compute the next position of Jupiter next month. Do you even know where Jupiter is now? I don't. Use calculus to do it, by the way. Could you do it by any means? I couldn't. They did it. And here's what they did. Something like this. So, I've got yield y equals f of x. Here's y, here's x. I've got a function. Input, output, represented as a graph. I've got, let's cut it off a little bit earlier. Let's say A to B. I want this area right here. Find the area under y equals f of x between x equals a and x equals b. Now let's real talk now about like, if the stuff I'm putting up here, if like the idea of a function is just really upsetting, and that's okay, it could be. It's upsetting to a lot of people. If what I'm talking up here sounds like gibberish, come see me after class because you might need to be in Calc 1. Especially when we start doing derivatives, and there is no shame in that. There is shame in like not being honest with yourself about where you're at and what you need. I will help you. We will get you to where you need to be. But if by the end of this day you're like, I don't know what the fuck just happened, maybe we should get you in Calc 1. Or maybe pre-Calc. I don't know how long it's been. Your education is too valuable to just wing it, right? You want an A. You want to get an A out of this. You don't want to just sputter through and hope to Christ for an A, a C, or a D, right? You want to do this in style. And you'll need to understand to do that. I don't know why I'm looking at these. There's nothing in there for me. So, we want that area. Here's what we're going to do. And this is one of the most beautiful stories I know. And I know a lot of beautiful math stories, but this is really, really one of my favorites. We're going to cut this axis up into pieces. Dot, 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 because I don't know how many pieces. So this indicates what's called a partition. So step 1. Cut the interval A to B. So this is a closed interval, indicating it's a range of real numbers, including the endpoints. Cut the interval A to B into n pieces. And the way we do this is by picking points. We make a partition of the axis by choosing points x0, x1, on up to x sub n. inside the interval. Now x0 is going to be the left endpoint. So x sub 0 is going to equal a. Let's mark that off right here. So here's x0. x1 is the next one. So here's x sub 1. Here's x sub 2, x sub 3, all the way down. B will be x sub n. So x naught is equal to a, and then x1 is a point to the right. That's a less than sign. So x1 is to the right of x naught. And then x2 is to the right of that. And I go all the way to the very last one, which is b. It's the right endpoint. So this is a partition. Pick a partition. Notice that makes intervals. The partition creates little bases for lovely little rectangles to go. So those points make little bases for rectangles. That's the key thing here. This produces n subintervals. And they kind of look like this. There's x naught to x1, there's x1 to x2, all the way up. Now this notation I'm going to use here, let me know if it makes sense. This is x sub n is my last one. See, I have to use n because I don't know how many cuts I made. And we have to do this in general. So if n equals 3, here's what that would look like. Let me just show you real quick. So if n equaled 3, this would be x0, here's x1, maybe here's x2, and then here's x3. So if n equals 3, we got a situation like this. Notice how there are 3 subintervals, 1, 2, 3 inside them. And the points of the partition are the endpoints. So here we've got n subintervals, and they kind of look like this. Here's x naught to x1, x1 to x2. And so this is x sub n minus 1 to x sub n. So in other words, if this was like x sub 17 here, this is 1 less, it's x sub 16. This subscript notation, you might not be super familiar with it, but you will be really strong at it by the end of the semester. Okay, so this produces n subintervals. Step 2, inside each subinterval, I'm gonna have to get knee pads. Subinterval, my knees hurt. Wear out these nice pants, for God's sakes. I hate buying clothes. Inside each subinterval, choose a representative point. So well, let me write this up here. So when we were doing our first experiments, the representative point, the first time was the right endpoint, then the next time it was the left endpoint, but it could be any point inside there. And that might even be a wiser move. So inside each subinterval, pick a representative point, x sub I star. Notation. And this is the shit you show your friends. Here's what I did today in class, and they're like, wow, that's heavy. Wait till you see. You'll show, you gotta have some shit to show your friends. If you want to share. They might not want to see. Inside subinterval, choose a representative point x sub I, and here for I equals 1, 2, on up to n. So we're going to choose n of these. 1 inside each subinterval. And so when I come over here, let's do a zoom in here. Here's just a small part. Here's x sub I minus 1. Whoa. Wow, that ground is unstable. Here's x sub I minus 1. Here's x sub I. I'm going to choose inside here x sub I star. This would be the ith interval. So this here is the ith interval. This probably all seems a little awkward and maybe uncomfortable right now, and that's okay. As long as it's not too freaky. If you understand what a function is, you're probably going to be okay. So I'm going to use that point to determine the height of my rectangle. This is all about rectangles. I'm going to use the value of the function at that representative to decide how high my rectangle is going to be. You're going to want that picture there. So inside each subinterval, choose a representative point. That's step 2. Step 3 is use the value of the function at each representative to get the height of the rectangle. This is nitty-gritty. Not every day is going to be like this. So come back, please. This is not every day. You got to see this once. Everybody's got to pay this price once. Today's your day to pay the price. The height of the rectangle. So that's going to look like this. F at x sub I star equals the height of the ith rectangle. What is the base? I've been talking. How wide is this base right here, just in this picture? What is this distance? How would you find it?
xi minus xi minus 1.
Beautiful. It's the right end point minus the left end point, right? If this was 7 and this was 2, the distance would be 5. 7 minus 2. So it's just, you gotta get the abstraction game going. But the width here is going to be x sub I minus x sub I minus 1. It's the difference between the two ends. So let's go to step 4. Step 4 says, since the base of the ith rectangle is, now check this out, delta x, that's change in x, it's the ith point minus the one right before it. So this is just subsequent points, the distance between them. And so this is the base width. This delta in calc and science is always about change. It's the change in x over the ith interval. So this is the base width of the ith rectangle. And now we're ready. What is the area of the ith rectangle? The area of this rectangle right here is this height, which is f at the representative, times the base, which is delta x sub I. So this width times this height gives me that area, and I'm going to write that up over here. So the area, so and area of the ith rectangle is height, that's f of x sub I star times delta x sub I. That's the area of that rectangle over there. I'm going to add them all up. All the areas, I'm going to add them all up. So add these all up. Step 5 is add up all these rectangles, all these areas. And so it's going to look like this. The first one's going to look like this. X sub 1 star delta x1. So this is height, base of the first rectangle. Height of the second rectangle It's the height of the function wherever we picked. Delta x2. I'm gonna have to wipe down again, Carter. I'm gonna be have to like scrub those freaking things all over me, like bleach my clothes. And then this is the last one, fxn star. Delta x vector. Add them all up. That's dot 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 showing we don't know what's here. Let's get some beautiful notation. Hopefully you saw this in Calc 1. If not, you're gonna get real good at using this as well. So step 5 can be summed up like this. No pun intended. You're probably not in the mood for puns anyway at this time of things. So in compact notation, this is the sum. So I put a capital Greek sigma. This means sum. It's the Greek letter S, stands for sum. Sum, as I runs from 1 to n. 1, 2, 3, all the way up to n. And then here I put the general term, f of x of I star, delta x of I. This is a Riemann sum. Time for me to get the ambulance. And it is approximately the area under that function. And this is approximately the area under the curve. Let me let you get caught up. That was lickety split. The way to get a better approximation is to get more rectangles. So let's make a little note of that. As n gets bigger, this approximation gets better. If I just let n become infinite, I get the precise answer. So as n goes to infinity, there we go, there's infinity. It has to show up in a calculus class. As n goes to infinity, this sum approaches the true area. Which is denoted by the following symbol. The sum sign, the sigma, becomes this beautiful S. That's an integral sign. S for a reason. It's a curve because it is a sum. And we started at A and we went to B. That was the range of the x values. The f of x of I star just becomes something much less intimidating, just f of x. And the delta x becomes dx. So, this is called the definite integral. Yeah, that's just denoted. The definite integral of f of x from A to B. Here's the best news you're going to have heard all day. You won't have to do what we just did. The whole first part of this class is to how to find these without going insane, more or less. So this thing right here is an integral, a definite integral. But what I want you to know, and here's why you had to pay that price. We all have to pay this, it's like a blood sacrifice, right? You have to pay that price so that you understand when we're doing some simple things with this, all this is going on under the covers. We're going to do some simple things. In fact, let me show you. Let me see if you refresh your memory. So how do I do that? So I got a definite integral. Let's do an application. So let me just put a little note here so it's at least in writing. I can't be sued or anything. But you won't be doing that. Exclamation point. Make sure, like I'm not messing around. That's for real. Instead, what you'll be doing is this. Find the area under y equals x squared from x equals 0 to x equals 1. Yield parabola from 0 to 1. What I want is the area underneath here. That's y equals x squared right there. I want that area. So first off, I could just write the expression representing that area as follows. So the area is going to be the definite integral from 0 to 1, the range of x values, my function x squared dx. That's the true value. Does anyone remember how to do that? Because this was like your final, in my class, this was your final, right?
Did you get the antiderivative?
Oh, you're good. Yes, ma'am. You take the antiderivative. We use the fundamental theorem of calculus. So all this craziness is just under the rug. It's under this filthy, disgusting rug with weird wet spots for some reason. We don't get under there because God help you if you will lift this carpet up. Poor you. Get a hazmat suit. Because it's probably asbestos carpeting on top of it or something like that. So how do we do this? As Olivia said, we take the antiderivative and then do some stuff. So to find this, we use the fundamental theorem of calculus, part 2. I'll tell you what part 1 is on Wednesday. The FTC part 2, which says to find this thing, what you do is you find an antiderivative. So this f right here is an antiderivative of the integrand, the function inside there. In other words, a function, big F, whose derivative is little f. So it's differentiation backwards, antiderivative, and you evaluate it from A to B. In other words, you plug in this limit, and you subtract. So there's some subtraction there. But the rest of it was all like adding. Like the real shit going on under the covers of multiplication and adding. So, what is the antiderivative of x squared? Well, we got some rules. So let's see here. Let's just make a little function. Here's f of x. Here's an antiderivative. We'll come up with a better table on Wednesday. But if I'm x to the nth power, how do I find the antiderivative of x to a power? John?
You're going to add 1 to the exponent and divide by the exponent, the new one. So it's x n plus 1 over
Beautiful. That's beautiful. You got something out of that class, man.
n. Yeah.
Yeah.
I think I can do decent.
I think you can. I know you can do decent. I know that. I know some things about you, and I know that much. So an antiderivative, just add 1 to the exponent, divide by the new exponent. So here, add 1 to the exponent, divide by the new exponent, do that from 0 to 1. Notice that notation means I still have to evaluate. So it's 1/3, plug in the 1, plug in the 0, 1/3, whatever our units are, squared. That's the area under that parabola. That's freaking awesome. That's exact. That's so beautiful. I got a little handout where I do this with Riemann sums. To entice you to come back, I promise to share that with you on Wednesday. So don't worry, you won't miss it. That's enough. Good God. What a day. Okay. So that's what this is going to be like. If that's working for you, please come back. If this isn't working for you, let's talk. Oh, and I never got I'll get a like name sheet on Wednesday. Thank you. So, is Carter, what should I go? Blue is what you prefer. Okay, I'm so sorry. Okay, cool. Because you told me, yeah, it's cool. I just want to make sure I'm on the same page. Okay, blue, you got it. Awesome.
Talk to you later.
Talk to you later. Yeah. That was mostly it, yes.
Which was what happened this summer too, because of what I said.
Did you want to talk, Josh?
Oh, no, I was looking at the board.
Okay.
Yeah.
Okay, I was gonna say, just hold on, we can
Yeah,
chat.
I didn't know what you put right here, but I was in.
Yes, sir, okay, awesome.
So I actually like, because of the fact that I did the class, like even though I didn't finish the class,
Wait 1
but,
second. Do you have that?
I do have all of the notes for all of the class already. So
Cool.
I wanted to make sure that like that what I have is going to be okay, and that like it's not going to be like throwing curveballs and like new formulas for like the same stuff. Because
Shouldn't be at
a
all.
lot of people use like different variables, and that stuff confuses me a lot. Because for Newman sums,
Riemann sums.
Riemann sums, yeah, we didn't do any of that because we just dropped right into
Yeah, I'm sure.
Antiderivatives. So I was like really confused for the whole class. So I want to make sure that like that stuff won't happen because it tends to like unravel a lot of stuff that I do know.
Well, I can't guarantee that I will teach it like the other person will.
Yeah,
In fact,
I'm
probably not, but.
I mean in the sense that like
So are we all just
Yeah.
sitting up front?
I wanted to ask this with all the forms I have.
Because
Sit in the back.
It's just
it'd be kind of weird not.
I mean, oh yeah, I mean, this is all standard. Your
Yeah.
teacher just
This
is
is
going
so
to. the
cute.
Just as
period.
far away from
But we
each
will
other
be
as
It
possible.
is, and I just took a picture of it the other day, same position, but just,
Yeah, when it comes down to it, that's gonna be what we're
she's so
doing. Trish, my part,
Thank you.
How'd she do on the
all
flight?
that stuff.
Oh my god.
It'll be very classic.
She did great.
Hi.
Sugar.
Yeah.
So, I just
Glad
wanted
we're
to
not
talk to
She,
you about your final grade.
it was just cold on the way back.
No, don't be
And I was like,
No.
are you okay? But I'm like, she has a full coat of fur.
I know.
I was worried that
Like
Artie's
that
hot
hurt
because he's so
me.
long
And it
hair.
probably hurt
Like
you
I'm
too,
always
because you were, but I
checking
was
on to see if he's
I don't know what
I
happened.
know. Well, every time I would touch her, she would like meow, and I'm like, okay.
You know, Artie is like, if you barely touch the top, he like pops his
I
whole
wasn't
head out and he's
pissed,
like,
I was-
oh, are we playing? I'm like, no,
Hey,
we'll go
it
back
was
to
sad.
sleep.
I wasn't pissed. I was just like.
I did forget.
So,
But I did the one with the final.
You
did have conservation
You did so good, and
restoration.
that was what
I think I
What
But
is that?
there was
What
other
is that?
people to see, and I couldn't like.
Oh,
treat
the,
think-
this
Yeah.
teacher,
special,
yeah.
even though I wanted to.
Yeah.
It's just
It's
like-
not Taylor.
Yeah. Okay.
You're okay.
So I just wanted
No,
to talk about
it's not
that. That's all.
Taylor.
Oh,
Taylor's
no, you're
in
fine.
New Hampshire.
I was happy with my grade.
Yeah.
Okay.
PhD
Wait, what class is
program.
this?
In my heart, you had it.
This is
colloquium.
colloquium.
I
Oh.
think you gotta be.
Which I printed out a cover letter.
If you see me, it's colloquium.
I'll try. Okay.
any of this semester.
I printed out a cover letter, but I don't think we have to have the cover letter until Wednesday.
Alright, I'll see you
No,
on
we don't need it
Wednesday.
till Wednesday, but I was gonna ask y'all,
Question for you is,
did we ever have to print out the job listing?
No, because remember,
um,
we didn't have, we just did it and then no one ever gave us feedback.
So even in colloquium, when
Oh, no.
John was teaching it, he didn't
Is
make
it
us
Daniel's
print it
part
out.
that we're going to the
Messages for
whatever
reference.
we were talking about this morning?
Well, the problem is I wrote that a year ago and
Conservation
that job
restoration.
listing's not there.
Bell part.
Bell part.
Oh, well, I just did a
If,
cover
like,
letter
everyone
for the
wants to,
job that I
like-
had,
I would love that too.
which is like a shit cover letter, but I was like, I got the job, so.
I have that one, but she makes me like rewrite it. I found another job listing like similar to it. And she's like, no, pick another one, that's fine, 'cause I have to start like